Good afternoon, everyone. My name is Dale Brosius. I'm the Executive Vice President and Chief Commercialization Officer for IACMI Composites Institute, and this is the June 17th edition of Innovation Insights. Thank you for joining us today. Wherever you are, I hope you're staying comfortable, whether that's staying warm or staying cool, but because we certainly have a heat wave in the middle of the U.S. right now. But it's summer, so we are in that season. So just to start off with a couple of things, just to reiterate IACMI's broad value offering around the theme of convene, connect, and catalyze with facilities, expertise, training, networking, projects, co-funding of projects, and other education. And if you're not an IACMI member, and we certainly appreciate those of you that are IACMI members that attend these events, but we know that some of you are not yet. So we encourage you to go to iacmi.org/members and apply for membership there, or start the process of applying for membership. I'm going to remind everybody we have the summer members meeting coming up in 2 months. So we will have Innovation Insights in July on July 15th, but we will not in August because of our members meeting. And it will be here in Indianapolis, where I'm located, and where the U.S. Olympic swimming trials are right now located. Busy days. Main slate happens on Tuesday, Wednesday, Thursday. I'll go into a little more detail of that, but the Wednesday, Thursday, the main speakers. The Tuesday is working groups, workforce development meetings, and a tour of Purdue, plus a special event. So we'll have the working group meetings all through the morning until 1 p.m. on Tuesday, one more working group in the Future Mobility and Vehicles Technology early on Thursday morning. The afternoon of Tuesday, we'll load up on buses and we'll go up to Purdue, about a little over an hour away from the meeting site, and see the Composites Manufacturing Simulation Center at Purdue, along with the 3D Experience Dassault Systems Center there. So lots to see there in terms of manufacturing equipment, modeling, simulation, and other great innovations. We'll come back from Purdue, and there will be a welcome mixer at Victory Field, where the Indianapolis Indians play. It's about a block or so away from the hotel. We've got tickets for that for those attending the members meeting, as well as beverages and refreshments on the Corona patio. So you'll have both, seats as well as food and drink. And on Wednesday night, after the main slate is over, the long day of Wednesday, when we have lots of presentations and participation, great networking reception at the Indianapolis Zoo, great pavilion there, plus opportunity to see some critters. So we look forward to those of you joining us there. Just a reminder that all this webinar is being recorded, and all previous webinars are on the IACMI website. They've been recorded. If there's anything you missed and you want to go back and catch, or if you want to catch something that happens today, or refer a colleague today to what we're recording today. So we've done over 31 episodes in the last few years, featuring over 85 members and partners. You do have to be an IACMI member or core partner to present, but the webinar is open to anyone to attend. Today we've got a great lineup. 2 great speakers, Eric Haiss from IDI Composites and Brian Rice from UDRI. So I'm going to turn the stage over to Eric now. Eric's the Global Director of Automotive Business Development for IDI Composites International. So I will go and stop sharing. Get to it. Okay.
How's that? Can you guys see the screen all right?
Yeah, to see the screen, just need to put it in the slideshow mode.
Oh, it shows.
And I'll mention that if you have any questions, there is a Q&A panel or the chat panel that you can put your questions into.
Does it look like it's in slideshow mode now, Dale?
No, it's not. So you can either duplicate the slideshow or...
Okay. Yeah, I was just trying to do that. Sorry, we had it locked down before, and now we don't. So let me try it again.
No. There you go. Good
okay,
to go.
Good. Hello, everybody. Thank you to IACMI for inviting me here. Thank you, Dale, Kim, and Jessica for working with me on this presentation. I just want to take a couple moments and introduce everyone to IDI Composites. If you're not familiar with us, IDI is a thermoset composite manufacturer. We're privately owned and headquartered in Noblesville, Indiana, where Dale is sitting at today. But we are a global company, so we have locations in Europe, in Asia, and in North America, as well as a sister division, Norplex Micarta, which also operates in the thermoset industry, but in a slightly different set of products there. Our core markets, we started in the electrical, so IDI is dielectrics is what the D stands for there. So we started in the electrical industry, but we have now diversified into a broad scope, spectrum of different markets, including infrastructure, transportation, and construction. And so we're pretty well diversified across all four of these, which has been very helpful as we've gone through the last few years in tumultuous times with supply chain, COVID, et cetera. But also as we see different trends, for example, electrification happen in the automotive industry, our electrical background has been really beneficial for us to respond to those requests from our customer base in that case as well. Some of you may know, and some of you may actually have visited this facility. So we are currently moving into a brand new facility. It's just a few miles east of our current facility. Our current facility is in a downtown area of Noblesville. And there were some infrastructure projects the city had planned that essentially forced us to move into a new facility. So we have custom built 120,000 square foot facility that is dedicated to SMC and BMC production. It will roughly double our current capacity of SMC production. And will include 2 new SMC lines, 60-inch width, and we will be upgrading one of our existing lines and putting it back into production for a total of 3 production lines. And we'll also have a couple of development lines available for new products and co-working with customers. So construction is complete. We're actually running early lots of material from the facility now, and our employees are moving from one facility to the new facility currently as well. So really exciting times for us there, and just an indication of the commitment that IDI and the Tom Merrill, that the Merrill family has to the composites industry. So we want to start off with this. Customers for a long time have known SMC for the performance it provides, its ability to design complex parts, the thermal capability of SMC, toughness of SMC. So there are a lot of features customers like, but in the wake of recent sustainability developments, it's been facing a headwind because of the thermoset nature. But it's important for us to recognize that SMC has 2 other features that may surprise you. First is that SMC does have a low carbon footprint compared to other materials. And also SMC already has recycled content in most cases, and the product itself can be recycled. So there's good information on both fronts of those, but today our intent is to talk about the low carbon footprint and how it compares to other materials. So in 22, IDI started to get inquiries from a variety of different OEMs in automotive as well as in the electrical side of our business regarding carbon footprint and sustainability in general. And so we started to look at our knowledge base internally and recognize that although we had some history with recycling SMC and BMC products previously, we really didn't have an expertise around sustainability. And we needed some outside help. So we launched a multi-phase global project with Forward Engineering, with Adam Hall's band here in the Detroit area, as well as his team in Munich, Germany, to better understand sustainability and how that would impact our products, as well as global warming potential of other products as well. We're not progressing here. Here we go. So after some introduction and training Forward Engineering did for our team, which was really valuable, they recommended that we do a top-down cradle-to-gate life cycle assessment. So what does that mean? So essentially, we looked at the carbon footprint or global warming potential of our SMC materials, as well as BMC materials, but focused initially on SMC, looking at the energy consumed within the facility, as well as all the raw ingredients, et cetera. And we came up with a cradle to gate global warming potential for our SMC products. And so cradle to gate means that this is the carbon footprint for a kilogram of SMC that is packaged and ready to ship at our dock. So that is the gate, if you will. So the cradle means that we include all of the embodied carbon for all of the raw materials that come in, whether it's the fiberglass, the resin, the packaging, the fillers, right from whether it's the mine or the initial oil production needed to make those raw materials. All of that carbon is included, including the transportation to move it throughout the supply chain into our facility, as well as all of the energy waste, et cetera, that our facility uses and or generates to create that kilogram of material. So this is an important point. So when a customer buys a kilogram of SMC, they often want to know what that global warming potential or carbon footprint of that product is. So this is the type of study that we would have to do. And here, this is the results of that initial study for our Fortium product, which is our truck bed SMC. And you can see here that we have 2.5 kilograms of CO2 equivalent. You guys still hear me? Dale, can you guys hear me?
Yeah, sounds good, Eric. Thanks.
Yeah.
Kim, can you hear me?
Yes.
Yes,
Okay.
you sound great.
Sorry, yeah, I just lost power. So luckily I have a backup power supply. So that's why I got darker. Sorry about that.
It's all good.
Okay, as long as you guys can hear me, then we'll keep going. So we have 2.5 kilograms of CO2e, which is equivalent. So not all emissions are carbon dioxide, but we do have a method of basically translating them into carbon dioxide. And so that's why we mean by equivalent. So CO2e. And what's important here, when you look at this pie chart breaks down the sources of that CO2 equivalent global warming potential. And most of that is coming from resin and glass. Very little of it actually comes from the electricity that we use in our facility or the plastic packaging, which most of which is recycled as well. So this is an important thing for us to understand as we looked at that and started to plan on what our next steps were for improving our products. We've since done top-down LCAs for about almost 30 of our products now, including different BMCs, SMCs, carbon fiber filled products, glass fiber filled products, et cetera. So we have a wide variety of different global warming potential data that allows us to understand how do we make those improvements to products going forward. Now, if you look at the next question you might ask is, well, how does the global warming potential of SMC compare to other materials? And here you have a comparison of some materials that we are often competing against for different applications. So steel is a little bit lower on a kilogram basis than SMC. Aluminum is quite a bit higher. And then we have thermoplastics. This is a polypropylene product that is, we've got both a LFT pellet as well as an organic sheet. So depending on the product, we compare pretty similar to the thermoplastics. But this really does not provide the full picture for decision makers. So it's easy data to understand and digest. But what's a little bit more tricky is to understand what happens further on down the supply chain and the product process. So to do that, we have to move from a material level LCA, which we just looked at, to what we call a system level LCA. And so for a truck bed, for example, this application has a lot of demanding requirements. It's one of the favorite applications for SMC. Works very well in this application, and you can see why here. So that application requires toughness, strength, abrasion resistance, UV stability, and SMC is very well suited for that. But it can be made in other materials as well. Steel, aluminum, even thermoplastic could potentially be done, although it's, other than the carbon fiber application that's currently in production, there's not one that is already there. So it's this is what we're trying to understand, is how do these materials compete against each other in an application like that. So one of the things that we do is each material has different densities, also different mechanical performance, and it's important that we consider all of that when we design an application, a complex application like a truck bed. And so one of the ways we do that is through FEA. So we, along with forward engineering, worked on 4 completely different designs that were focused on each of those materials. So we took advantage of the strengths and also tried to design around some of the weaknesses of each of those materials to come up with an efficient production representative truck bed, so that we could compare that carbon footprint of each of those. And to make sure that we were in the right thicknesses and right designs, we used FEA analysis to do that. And here's an example of one of the tests that we did in FEA, which is a 30 kilogram block that was dropped from a 0.6 meter height, so that we could compare how the impact of that block happened with those beds. In order to come up with this list of criteria that we used for the design phase of these boxes, forward engineering and IDI went to several different large OEMs with a list of criteria that we thought were relevant and asked for their input. And so we feel very comfortable that we have a good understanding of the key design elements of a production intent truck bed, and that these designs really represent that. So here you can see actually 4 different designs. So the leftmost is SMC. You also have steel, aluminum, and then the thermoplastic design. And so some of the differences that you might look at is all of these beds have trunk wells in them. We found that most consumers prefer to have some kind of a bed well there. They like that feature for as a cooler or for storage of products, etc. However, in the metals, it's not as easy to integrate that type of feature. So we looked at ways to minimize the impact on a metallic application or implementation. And so you may see that we reduced the size of the opening slightly. And also you may note that the actual well is made of SMC in both of these cases. And that was done because we found that SMC was a more efficient way of making that well than if we had stayed with steel or aluminum in those designs. You may also see that the panel breakup is different. So the different shades of colors indicate the different panels that were done in the design. And so, for example, here you can see the steel sidewall is all one piece because steel can be drawn relatively deeply without needing additional steps, where aluminum, on the other hand, struggles with depth of draw. So you have to create the wheel well from a separate piece. So you'll see these types of features as well as different wall thicknesses on this page. And the other thing we did relative to this is go out and look at the aluminum, the steel, and the SMC applications that are already in the market and make sure that our data was correct. So we feel very comfortable with these designs. And once we had those designs, sorry, let's get back here. If it'll let me go back. There we go. The next step was for us to go through and create a very detailed bill of material as well as bill of process for each one of those designs. So these are just some screenshots of some of that, where we're looking at right down to the cross members, the fasteners, the seam sealers, the E-coat, spray-on bed liners in the case for the metal applications. And we create that list of materials that are needed, as well as the different processes, whether it's stamping or painting, et cetera, that are involved. And then once we had those lists of materials and processes, we went and looked up the appropriate life cycle information for each of those products, and it's called a life cycle inventory. So we have a full list of not only what those values are, but where we got those values from. So we use third-party verified data in every instance, so that we feel we have the latest information in a very comprehensive, detailed study. And from that, here are the results. So as you see, SMC at 725 kilograms CO2e for a truck bed is the best, the lowest carbon footprint in the different, across the different materials. And you can see these numbers include the use phase, which is the kind of orange color at the top here. So that includes a 200,000 kilometer life cycle that is there. I believe it was a 10-year period that we were studying in that as well. We also looked at, this is cradle to grave, so we're including end of life. So you will see here, the green is an end of life section that's result is the carbon penalty, if you will, it takes to recapture those beds, grind them or post-process them into something that can be reused, as well as recycling credits that come from how those materials were used, whether they were to replace their virgin materials or whether they might be replacing another material in another process. So very comprehensive design. And one thing that is interesting down on the bottom here, we've shown again the carbon footprint of each of the base materials itself so that you can compare. And you can see here that even though, for example, steel has a very competitive footprint on a per kilogram basis, the final result in the system level LCA is quite different. So this is why we felt this study is really important. We're going to continue developing this study and with the intent of peer reviewing and publishing this study a little later this year. So we're in the process of setting up meetings with OEMs to review the full detail of these calculations and analyses. And once those are complete, we'll prepare a paper and present that. So today I also wanted to add some new information that if you've seen this presentation, this would be new for you. One of the questions we got asked often is how does the transition from internal combustion engines to electric vehicles affect this study? And so here's some results of a study that Forward Engineering did. They call it a sensitivity analysis. And we look at, again, the same life cycle, 200,000 kilometers, but using an electric vehicle instead. And so this would assume the standard US grid electrical carbon footprint. So this would vary, for example, if we were in Europe, which might have a little lower carbon footprint. It could vary region to region. If you have an area like the TVA, Tennessee Valley Authority, that has a lot of hydropower. So there are different reasons why this could vary. But if you look at the average electrical grid in the US and the carbon footprint from this, you would see these types of results. So the overall numbers do come down when you look at the carbon footprint. But the ratios more or less stay the same with electric vehicle versus internal combustion engine. So right, going to one more slide here. So just to talk about next steps, I mentioned briefly that we are meeting with OEMs, setting up those meetings now, and intend to do that here in the next month and a half or so to get their direct feedback for the detailed information. Then we plan to publish a peer review paper later this year. We have to get the word out. So thermosets, and I would say composites in general, have a really great story to tell. So it doesn't mean that in every application, composites, SMC, for example, is the right material, but in those applications where we do offer some strength, toughness, scratch resistance, etc., we do have a very compelling carbon footprint as well. And so we can be a very sustainable product in those types of applications. We are also continuing to work on methods that will improve our carbon footprint. For example, we've done quite a few things in our new facility to reduce the carbon footprint, energy utilization, waste streams, etc. And we're continuing to look at recycling options, methods, increased use of both recycled and bio-based materials for our products. So there will be a lot more coming out on those fronts in the next, say, year and a half or so. But anyway, we want to keep getting that word out. and inviting those that have interest in this topic. I'd love to talk about it. Very happy to discuss that with you. If you have any questions, I'd be happy to take them now. Thank you.
Right. So I'll just remind everybody, put your questions in either of the two panels. We'll pull up the. Yes. We've got a question. Is where do you plan to publish your peer-reviewed paper?
Sorry, Dale, I can't hear you.
Kim, am I coming through?
I can hear you just fine, Dale. Eric, can you hear me? All right, he can't hear me either. I will send him a message in the chat, and what we can do is make sure those questions get to him that way.
I don't know, maybe his power came back on and so he's muted.
I'm working on that. We try it again.
Dale, can you hear me now?
Yeah, we can hear you. Can you hear us?
I think we're going to have to move into doing his questions online. So I'm going to send him.
I can hear you guys now.
Okay,
Great.
you got it.
Here we go.
Okay, sorry about that, guys.
Maybe your power came back on, whatever happened. Okay, so question was, where do you plan to publish your peer-reviewed paper?
Great question. I honestly, I don't know that answer at this point. So I'm working with Forward Engineering on the process to do that. We will be presenting, or we intend to present at the SAE World Congress in front of a wide variety of material groups there, so that we're very open about the study.
Okay, and then what assumptions did you make about recycling of SMC?
Yeah, great question. So this particular study was done using a cement kiln processing of the waste. So we essentially were grinding the SMC end of life and then using it to replace silica as well as some fuel for the cement making process. So there's actually a very compelling argument on that front. We know that it's not been a real popular method. It's not getting as much attention as it once was, but it is a method that has been used and continues to be used for SMC end of life today.
Sure.
So we have companies in Mexico that are doing that. We have also, or are also looking at the idea of grinding SMC and putting it back in to replace some of the filler. So we have some data on that as well that also looks good for SMC. Actually lowers the carbon footprint slightly when we do that as well.
Okay. Speaking of carbon footprint, on the LCA, what was the database for the LCI?
There were a variety of different databases. I would say most of it came from Sphera or Gabi, which is one of the more popular ones. But there were a variety of different databases used, and again, that'll be published in the peer review paper.
Okay, and last question I've got is what I didn't see mass values unless I missed it.
No,
I
we
saw
did present
thickness
the mass
differences,
value.
but but I didn't see the mass values.
So I would say that the steel was the heaviest. SMC was the second lightest. Actually, aluminum was a little lighter implementation than SMC. But I would say the SMC, the thermoplastic, and the aluminum were very close to each other, and then steel was a bit heavier.
Okay.
The important thing I want to mention, Dale, the thermoplastic, we did a design. We feel good based on the FEA that we did. But in actuality, there's not that kind of a design done. So the sidewalls have been done in thermoplastics previously, but the actual bed floor itself has not been done other than in a carbon fiber implementation, which would be quite a bit more intensive from a carbon.
Of course, yeah, that would really drive the.
Yep. But we felt it was important to include it because it is a competing material. So we wanted to understand that data for ourselves as well.
Okay. All right. So thank you very much. If there are other questions, put them in the chat or the Q&A, and Eric can get to those. Eric will be a panelist in a sustainability panel at our IACMI members meeting in 2 months. So we look forward to seeing you there again.
Thanks,
Okay,
everybody. And don't hesitate to reach out if I can be of assistance.
sure. Okay, we're going to switch over to our second presenter. And our second presenter is Brian Rice, Dr. Brian Rice, University of Dayton Research Institute. Brian serves as the technical area director for aerostructures and hydrogen and compressed gas storage at UDRI on behalf of IACMI. So UDRI is a core partner, has very many capabilities that Brian's going to go over and show some capabilities that they have, as well as outcomes of some projects they may have done for IACMI in the past. So Brian, over to you.
All right. Thank you, Dale, and thanks to everybody in the audience. Appreciate your time. Is my screen showing up okay, Dale?
Yes.
Okay. All right, good. So yeah, I'd like to kind of review UDRI, primarily focused on our advanced composites, but also include some of our capabilities and structures in general. So UDRI, we were established in 1956 to support the Air Force out at Wright-Patterson Air Force Base. As a result of that ongoing activity, roughly about $200 million a year of Air Force contracting, we are ranked #1 in the U.S. for materials R&D among colleges and universities. So that's obviously a big strength for us, and composites is a big part of that materials R&D. So I want to begin with just a quick video here that shows some of UDRI's labs and capabilities. So I'll kind of speak to it a little bit as it goes through, give it a little bit of narration. Obviously, most of it's aerospace composites, so autoclave. For those of you that may have...
Brian, if you're showing the video, you probably need to switch which screen is being presented.
I put it over there. You're not seeing it?
No. We still see the slide itself.
Oh. Well, I'll initiate it from my slide presentation then. Let's see how, okay. You're probably still not seeing it then, right?
Right. Yeah. You need to share, share.
You just share the window.
It's not showing right now?
Yeah. You need to share the other application, the web browser, or share your screen directly.
All right. I thought if I just put it over there, it would pop up, I guess. Okay. Now you're seeing it?
Yeah, you can just, yeah.
Okay. All right.
Thank you, Brian.
Right. Okay. Again, we'll just kind of go through this, about a 4-minute video. I'll stop it at a few locations that are relevant. Again, most of our work historically has been with the Air Force for aerospace. For those of you that were at IACMI members meeting January 2020, UDRI hosted the meeting, and we gave tours of our lab. So this lab here, some of you on the call may have seen before. It's gone through extensive renovations and additions and capabilities since 2020. So I'll try to highlight some of that. But anyway, I'll go into more detail on some of these technologies you see as part of my PowerPoint presentation. What you're seeing here is called tailored fiber placement. We had a number of projects with IACMI on that I'll discuss in the PowerPoint presentation, but that's a big focus of ours, is topology optimization, putting fiber in the load path, and then using the automation to do that. Then we did a lot of work with rapid clave using some rapid cure epoxies. This project here is one we did with Airbus, where we used TFP to make preforms, and then blend those with thermoplastics, put it in an injection mold and then essentially do overmolding to make clips and brackets. And then, of course, did all the simulation, both for the processing and the stress analysis. We do quite a lot of work with, again, analyzing when you have different fiber architectures and you're putting it in like an RTM mold or autoclave or what have you, to simulate what that exact fiber architecture is going to be. This is our autoclave, 5 feet by 10 feet. It can do thermoplastic, so it goes up to 800 degrees Fahrenheit. Some of what they're showing you here is doing some of the rapid cure aerospace epoxies and utilizing some low-cost AM tooling. This slide here is our current rapid clave. I'll show a video in a minute on the new rapid clave that is coming to UDRI later this fall. Reverse engineering with a laser scanner, create-form scanner, so we can take existing parts and develop CAD files with them. Here's a micro CT scan, so you can look at defects in fiber architecture of cured composites, and then of course mechanical testing, both at all through the environmental cycles, hot, wet, and that type of thing. Here's our large scale smart lab. So we do large structures. Then I think there's about 30 load frames in there. So we can do high strain rate as well. We had an IACMI project for automotive, getting high strain rate behavior, collision behavior of materials, if you will. And we have DIC technology. And it's big enough you can even test an aircraft wing in it. On this large structure, we're also doing large aircraft landing gear for life extension. When you visit UD, a lot of people like to see the impact physics lab. We have the fastest gun in the world that it's used for like NASA and so forth for simulating micrometeoroid impacts, as well as launching birds at canopies and that type of thing. So they're different guns, but there's what happens if a UAV gets too close to an airplane. That's why at the airports we try to keep the UAVs away from the aircraft. This is a high-speed video of a simulated bird strike on an aircraft canopy. So we do a lot of high strain rate, unique testing. This is our thermal analysis laboratory with all the your TMAs, DSCs, TGAs, etc., to characterize the materials. We have a pre-preg line and a thermoplastic extrusion line, so we can make films of different materials. Our pellets to part additive manufacturing printer. We can compound different materials and make the pellets for the winder. These are all the ovens and humidity cabinets and so forth that we use for conditioning composites for different use cases. Right here is this is our pellets to part Titan systems. So we've done quite a lot of work with carbon nanotube filled multifunctional thermoplastics for various applications, as well as printing tooling that might be used in the autoclave or rapid clave, for example. I think a lot of people now are familiar with that. But one thing unique that UDRI does is we make custom materials. But I'll spend a little bit of time on this. This was also the subject of several projects with IACMI, where we grow vertically aligned carbon nanotubes. And this robot was part of an automation project we did to demonstrate that we could produce at least 10,000 square meters of the vacant sheets that would go interleaved in between composites on an annual basis. And now that's being ramped up by an order of magnitude in the next couple of years, and then 2 orders of magnitude over the next 5 years as applications develop. I'll have another slide on this in a minute. Anyway, so that's the growth furnace. And I think that's it for that. So I guess I gotta close that out and all right. I'm gonna pull up another video here. This will be of the rapid clave. So I guess I gotta reshare. Okay, is that Dale?
Yes.
You've seen the rapid clave? Okay, good.
Yes.
All right, perfect. So this, we had quite a lot of activity with IACMI previously with Globe Machine to take the rapid clave that was developed for the automotive world, such as the Corvette body panels, and reinvent it, redesign it for aerospace. And so you saw that EDRI has a 5 foot by 10 foot autoclave. And what we have here now is a reimagined rapid clave that's also roughly 5 feet by 10 feet. So that way we can have a direct comparison. And this vessel has been built and pressure tested. Now it's going through, all the add-ons, all the electronics and all that type of thing. It should land in Dayton in November. But what's unique about I'll pause it here for a minute. What's unique about the rapid clave versus, say, an autoclave? An autoclave typically, you've got a heater in the back, a fan that's blowing hot air, and so it's purely convective heating. With the rapid clave technology, you can have a heated fluid, like a oil, a heated oil that can heat the tooling directly, which is usually why you have a slow ramp rates in an autoclave. The heated air will be projected downward rather than from the back like you have with an autoclave. So you'll get more uniform heating with the hot air as well. And you'd have the possibility, if you wanted resistive heated tooling or even IR type heating. So you're basically exploiting the four major means of heat transfer, so we can get heating rates that are consistent over 100 F per minute. So that way we can achieve rapid cure cycles. So as you can see, it's split down the side to make it easier for to automate the part placement and extraction from the rapid clave. So what you're seeing there is on the base over here on the right-hand side where my cursor is, all the process utilities get plugged in automatically, including thermocouple ports, vacuum ports, etc. So it's really designed to operate, much more quickly and efficiently and more of an automated mode than, say, an autoclave would be today. Kind of speed up there a little bit. So you can see how the clamping mechanism operates for the pressure vessel and how the door opens and closes and the tool gets placed in and extracted. So presently we're working with, at least 4 major prepreg manufacturers that have, high rate cure prepregs, primarily for aerospace, and running those in the current rapid clave and making demo parts and so forth. So let me share back to my. Okay, so this is back to my PowerPoint slide. So I'll kind of do a little bit deeper discussion on some of the things I just showed you. So again, here's the rapid clave. Again, we have what we call rapid clave number 1 is what we're using to process different Pre-preg materials and different tooling concepts today. Generally, you're looking at roughly a 30-minute cycle time based on the kinetics requirements of the materials that are out there for aerospace. Here you can see an idea of how you'd get four aerospace parts packed into the rapid clave here in the future, and I'll elaborate a little bit further on these representative parts that you see here. But anyway, it'll be installed around November. Definitely interested in anybody that's interested in IACMI projects in the future, taking advantage of that technology. A little bit about some of our design, because again, UDRI, we do the material science, we do design, manufacturing, testing, pretty much a full spectrum of services. BSAM is our high fidelity FEA model, so you can take into account the exact fiber architecture, layer by layer, and if you have inclusions or whatever, model all that. So it's what we'd call a local FEA model, because you get a very high fidelity damage progression based on the actual state of the material. We tie that in also with what we call topology optimization. So if you have your FEA model and you know where the stresses are, and you have a technology like tailored fiber placement that can actually locate a toe exactly where you need it, how would you take advantage of this, right? So here's an example where we were looking at if you had a sandwich structure, two skins with a honeycomb in the middle, which is a very lightweight, stiff structure, but it's not very damage tolerant. How can you make a monolithic skin but still get the same performance in terms of stiffness and weight using topology optimization? So this is an example of a wing skin where you've got on the upper wing skin, let's assume you have 25% or no, 75% compression and 25% shear. This geometry is what is idealized. And it's not quite AI, but it is an iterative solution. It's a self-optimizer, right? We don't have somebody designing it. We give them the criteria and the software develops it. And then we can use the Taylor fiber placement to actually render that design into the structure. And Taylor fiber placement remains, here in the US, it's not heavily used, but in Europe, it's actually been around for over a decade in production parts, such as the Airbus 350 window frames, for example. One IACMI project we did was, can we enhance the bearing strength of a hole in a composite, if you're doing attachment hardware and so forth. So basically, you're making this little spiral around reinforcement that weighs about 1 gram, but by just adding that, a gram's worth of composite, you got about a 47% increase in the load from 3,700 pounds to 54. So it's pretty significant improvements possible there. And we've done quite a variety of different structures using the Taylor fiber placement and topology optimization. I'm going to focus on this one here. It's a wing bulkhead for a UAV. So we had the load requirements, stiffness requirements. Our baseline was A&P Kiso braid. We wanted to see if we put in Taylor fiber placement stitched on top of the Kiso braid, what kind of weight savings could we achieve? It was pretty impressive. And we made several of these bulkheads, and then we designed a load frame here that it'll be tested in a couple weeks. And as part of the testing, we're going to have the DIC and strain gauges that will help us map what our FEA predictions were to the actual performance of the composite structure, because this is a very highly anisotropic structure with all the unidirectional fibers built in with the CCO braid. And this is just, we've got a latest state-of-the-art digital image correlation set up there that'll be helping us essentially get the full field of strain as we're doing the test. And then in terms of, again, trying to optimize automation and reduce time for ply layup and that type of thing, these kinds of parts are typically machined from aluminum because, frankly, the labor to do hand layup with pre-preg is very time consuming. It makes the parts very expensive. So we're showing using the latest software for ply flattening and Gerber cutter and designing the layup not just for the mechanical properties, but also ease of layup allows us to make it, something like this affordable using composites versus typically what would be an aluminum structure. Now shifting gears a little bit from continuous fiber composites, we acquired from Krauss-Maffei something called long fiber injection, which is essentially, it's a wet spray up, robotic wet spray up of chopped, what used to be, presently is glass fiber with a urethane resin. So for example, John Deere tractors utilize a lot of these parts or this process to make parts where you can actually do in-mold coatings and that type of thing. Our project with the Air Force and Krauss-Maffei and Lockheed is say, okay, we want a robotic process that's very rapid, essentially zero scrap, but we need more aerospace properties, right? We want carbon fiber, we want a high TG urethane, we want 50% fiber volume, no porosity, for the strength and stiffness. So that's what we're doing on this program now is spraying up carbon fiber with the urethane, and we're going through a different evaluation of candidate carbon fiber tows, and looking at different spray up patterns and so forth and so on. Later on, we have an interest to do a hybrid approach where you could take a preform, a continuous fiber preform, lay it in the tool, spray up your chop. We're going to have buildup areas, and then mold it. So very much it'd be like thermoplastic overmolding, but this is with a thermal setting snap cure urethane. And a pretty impressive deposition rates, about 6 kilograms per minute. So it's pretty fast process. Additive manufacturing, we've done a lot of work, both metal and polymeric, whether it be end-use articles or in this kind of area. We've done quite a lot for tooling, like a carbon fiber filled Ultem tooling for autoclave and rapid clave, et cetera. Also a lot of tooling just for even checking out for doing tailored fiber placement preforms. How is the preform going to lay out or nest into the tool to validate that? Also, in the area of low-cost tooling, working with the Air Force, there's a company, Makina Labs, that does what's called progressive metal forming. So they can take a piece of sheet metal and clamp it around the perimeter and then form that sheet metal into a tool or an end-use part. But the beauty of this is obviously you're not machining away a lot of material, right? You're just forming the material. And so if you make 20 tools, so you do really high rate production, it's going to be much, much cheaper than something like CNC machine tooling. And the tooling is very thermally responsive because obviously steel or aluminum in a rapid clave environment is very lightweight, so it can heat or cool very quickly. And then just kind of wrapping up here, we've done a lot of work over the years, 20 plus years, with multifunctional composites or nano enhanced composites. We've done a lot of work with IACMI on the vacants. So that's what you'll see here. So we have a project that will be starting with IACMI to make hydrogen storage tanks where you're interleaving the carbon nanotubes between layers of prepreg to enhance the properties, the fatigue life, minimize microcracking, that type of thing. And that is it. So I'll stop sharing.
All right. Thanks, Brian. Yeah, very comprehensive presentation, and sometimes it's good to go back and see the full breadth of capabilities that EDI has. And I know you've left some things out because I've certainly seen other things as well. But everything from materials development to the materials testing to the full scale testing and evaluation, it's always quite impressive. There's a question that's come in: does rapid clave produce, or has the rapid clave produced higher thermal stresses? So I think it's probably related to the quick heating and quick cooling. Does that result in higher thermal stresses than, say, an autoclave, which would be much slower in heating and cooling?
Right. So a couple points on that. We've taken several materials, some that were developed for rapid cure, like in a press, and some that have been historically used for autoclave. And number one, we did a material property database, and we saw comparable properties, but also in terms of any kind of part warpage. Again, we have our laser scanner. So we haven't seen any, comparing autoclave to rapid clave, we haven't seen any, dimensional differences, that might be resulting from part warpage or that type of thing. And we also did some work where we did a 90-degree flange to look at spring back, and it looked consistent. So we haven't seen any evidence that the rapid cure is causing additional thermal stresses.
Okay, right. Remind me of what would be the max part size that could go into the new rapid clave that you're getting?
Yeah, so when I say nominal, it's going to be less, but that it's on the order of 5 feet by 10 feet. Maybe subtract about 6 inches from that, and then the Z height is I think it's about roughly 24 inches high.
Right, obviously dependent upon curvature, of course.
Right, yeah, just like an autoclave, right? It's you never fill the whole autoclave with your parts. So.
Right, yeah, round parts and around around carrying them. Yeah, work perfect.
Yeah.
Okay, all right. Well, no additional questions are out there. So, we're near the top of the hour, and I want to thank everybody for attending. I want to thank both Eric and Brian for presenting. We will have our next episode on Monday, July 15th. Mark Morrison, our Vice President of Communications, will be doing a big, more in-depth presentation and preview of our annual members meeting at that presentation next month. So wish everyone a good Monday and rest of your week, a very productive week, and we will see you next month. Thanks.
Thank you.